I'm looking at basically, NE5532 op amp, exactly in the same configuration in the last video I tested with a TLO72. And yeah, I gotta admit, the TLO72 is more impressive, even though an NE5532 has a 10 megahertz bandwidth versus the 3 megahertz bandwidth of a TLO72. In fact, you can see what this is of the TLO72, what its spectrum is, and you can see, really, it falls down. Well, this is probably did. Oops, I did this at too high of a signal. Um, but anyway, its waveform. If I put the proper signal level in it, and that's a constraint of this generator. That's why we're getting an out of range error, because this generator doesn't like it if you put too big of a signal in and get too big of a signal out. It helps to put it in times X 10 probes, and just don't tell it or whatever. But I mean, but the fact of the matter is that earlier I did a signal that showed the 3x gain across the board, but this cuts it about in half at that injection level right there. But the point is that yeah, it does actually perform. It goes about the 3 decibel drop. A little over 1 megahertz for a three, a gain of 3 amplifier, closed loop gain of 3. So because again, its open loop gain cuts down to about 3 at 1 megahertz. So it's, but it does have, and it did perform. I mean, I actually generated an O72 out to about 3 megahertz. I generated, actually it had a gain still of just about 1 at 3 megahertz like it's supposed to. And you could still see, resolve a 1 volt peak to peak output signal. Um, so it was pretty impressive. um, I don't think I screen captured it or anything, if I recall, but yeah, this 5532 is a lot less impressive, because remember the 072. I mean, actually, I can go out to like 280 kilohertz at a 10 volt peak to peak output and still have it look reasonably good, at the 250 plus kilohertz. Here, I'm at, its official power bandwidth is 140 kilohertz at 10 volts peak to peak. That's why I'm testing at this level. I try to test all amps at that level to kind of compare it to this gold standard. But this NE5532 is a 10 megahertz bandwidth op amp with a slew rate of about 9 volts per microsecond. The TLO72 is only 3 megahertz, but it has a 13 volt per microsecond slew rate. So that means its slew rate bandwidth is going to be higher than this just because of that alone. But I suspect it's even higher, or this is lower than that, 9 volts maybe by a little bit. But this should have more gain. I mean, 10 megahertz. I mean, yeah, it should have plenty of of open loop gain even at 1 megahertz. But we'll investigate that here in a second. Um, but here I'm at 130 kilohertz on the signal, and you can see that we are, you know, got a gain of approximately 3 out of it, just under 3, and a 19.6 volt peak to peak output swing. So, but like I said, let's see. Now this is a sine wave, so what happens if I go higher in frequency? Well, even just up to here, we're up to 144 kilohertz. It's still 20 volts peak to peak, but yeah, I'm seeing definite distortion in this thing. And this op amp, does have input protection diodes in it. The TL72 generally doesn't. So, that's one main difference here. I only have like 3 op amps that have protection diodes in it. The NE5532, the TL, or the LM318, and I think the 308 does too. I'd have to check my notes. Um, but those diodes are in there, for latch up protection basically. So some of the older op amps would actually latch up, you know, um, if your signal difference was too high. So they're trying to prevent the op amp from going into hard saturation. I'm not sure if that's the input or the output. Again, I read about this a long time ago, but like 30 years ago, so I don't remember specifics, but I just know those little diodes are meant for some op amps, to have input protection. So your input signals can't differ by more than zero point 0.6 volts. And there's a lot of occasions when that can happen, including if you exceed your slew rate, because what'll happen is that if you exceed your slew rates, like at higher frequencies, for example, there can be a delay between your input signal um, and your response of your output, which means your feedback is going to be delayed. So that means your input signal actually versus its the positive terminal. In this case, this is a non-inverting amplifier, but your positive terminal, you know and the difference between it and the negative terminal may differ by more than zero point 0.6 volts, just because the op amp hadn't had time to adjust itself. It's like a PID loop, with too long of a delay, basically. But anyway, because of that, it can end up kind of clipping your signal. Those diodes, pesky diodes, can pop in, and not just in differential mode, but in because you cannot basically use a you know an op amp like this, with those input diodes as a differential amplifier. You can, as long as the signals you're comparing are less than zero point 0.6 volts, but you can't use it like a normal differential amplifier. You might be, like using your probes to probe some, voltage across a resistor that may be 10 volts or something, and trying to amplify that by a fixed amount, on the output, because you can make a differential amplifier that has fixed gain. Most differential amplifiers actually do, in practice have fixed gain when they're used as a differential amplifier. But anyway, because these diodes, now you just really can't do that. So you got to avoid op amps with diode inputs if you want to use them for any kind of differential application. But at any rate, um, those diodes can kick in and introduce nonlinear distortion, at a certain rate. I'm not sure that that's what we're seeing here, but we are definitely exceeding the slew rate, and let's increase the frequency. And now we're finally starting to really drop in amplitude. It's going 19, 16 volts, and we're at still 190 kilohertz, and it's looking like a kind of a distorted triangle wave now. So, like I said, let's back it off, below its power bandwidth, and now it's a good looking sine wave, but, its square wave is kind of a trapezoid. In fact, let's try a trapezoid. Wow, it looks exactly the same. Um, in fact, that shows you that's what the limit is. Now I can, like I said, I can't steepen it any further. Oh, this is annoying as shit. But I can narrow it. I can reduce its rate, but then you hit its limit. But see, if I reduce its rate, now you got a nice straight line on this thing. Um, but if I try to increase it too fast, okay, now we got distortion. That's kind of bowed out. This is kind of bowed in. So that's where a lot of this distortion's coming from. So, because like I said, that's why this trapezoidal waveform is actually really handy. But like I said, just looking at it and comparing this, square wave, I got it the wrong duty cycle. I wish you could set different duty cycles for different waveforms. That would be nice. Um, okay, but there you go there, and okay, that's what a ramp up looks like. I don't know why it's floating positive like that. That's rather strange. That's what the ramp down looks like, with the same basic settings. Um, you know, Pulse waveform looks like that. Um, so, which, is kind of okay-ish. But again, it's certainly a slew rate limit, that we're seeing here, and it does become nonlinear if it's too steep. So it's definitely slew rate related at this point. So we're at 107 kilohertz right now. Um, the sine wave looks nice and dandy, and the triangle wave, even the triangle wave, even with its low slopes, is still showing distortion. See, we got this annoying thing here and this annoying thing here, which I do not know where that's coming from. Let's reduce the frequency, you know, but again, because that's not a big transition. The TLO72, again, at this frequency, I mean, even 150 kilohertz, everything looks perfect. So, again, I'd say the TLO72 is a superior op amp, when it comes to, a higher fidelity reproduction of your input waveform. So, because even here, I can still see a slight little dip there and a slight little dip there. It's hard to see. If I zoom in on it, it's a little more evident. It's still hard to see, but it's there, and we're at 62 kilohertz. So, but yeah, it does get worse. I mean, here it's really bad, and we're at 116 kilohertz. And as we approach the power bandwidth, 144 kilohertz, it's pretty damn distorted. Now let's see what happens if we reduce the amplitude on this thing. Okay, that improves it quite a bit ostensibly. Let's see. But it's still actually there. I mean, if I, because we're at, 8 volts peak to peak instead of in the 20 volt range. But, it's still not a perfect looking waveform. And there's a square wave, which, is not half bad at 144 kilohertz. But again, 8 volts peak to peak, we're way below our theoretical full power bandwidth. Ramp waves, at least that's starting to look like an actual ramp at this level again. So again, slew rate's definitely limiting a lot of this stuff. So, but yeah, I mean, if you want it to, be at the 20 volt full power bandwidth range it's supposed to have, because again, we should be at that right now, but we get more and more slew rate distortion. So again, that higher slew rate, on the TLO72 definitely benefits us. And plus, it's a JFET input op amp, so it's got high impedance inputs too, which, is helpful in a lot of applications. So, but again, that's taking a look, at it, frequency levels like that. Let's look at it at like 30 kilohertz or so and see how things look. Again, let me make sure. See, got a sine wave. Let's get to 20 volts. Okay, there we go. Alright, so yeah, the sine wave, certainly looks good. Square wave, again, you can still see the slew rate being evident even at 30 kilohertz. It's actually a predominant factor. A trapezoid, looks perfect, at 30 kilohertz. Pulse looks quite good. That's a noise thing. The sine power, ramp up, ramp down. Triangle wave looks, excellent. I mean, but still 30 kilohertz, seriously? So anyway, this isn't as good to drive a, for a DAC output, for a 500 kilosample DAC output as a 072 is. So, I mean, again, in theory, it's got a lot of gain to work with. Let me look it up real quick. Yeah, from the looks of it, at 30 kilohertz, this op amp should have a gain of about 1,000 at 30 kilohertz, and an open loop gain, to work with. So we just got a gain of 3, so it should have a loop gain of at least 300, left. So, well, not 300, but 300 times that anyway. So we got way more than enough gain to linearize everything. At its power bandwidth, somewhere near that. Let's see, we got Here's about 100,000. So, well, actually, let's look at 1 megahertz. 1 megahertz, you got a gain of, eh, I don't know, 12 or so to work with, um, open loop. So, um, let's see. But at 100 kilohertz, you got a gain of 100, maybe 200, 250 or so to work with at its power bandwidth. So it's got plenty of gain to work with, especially since we got this set to a gain of 3. I mean, it's got plenty of excess gain, so that's not why it's nonlinear. It's not why we're seeing distortions completely because of slew rate at the very least. So, but let's go the other direction with this thing. Let's start. Let's go ahead and start really upping the frequency here. Let me change back to a sine wave. Okay, 100 kilohertz, 200 kilohertz, 300 kilohertz. Now let's go zoom in on this crap. Our gain at this point, is only zero point 0.6, but I'm still trying to drive it to 4 volts peak to peak output, but that's way too high. Obviously, we're at 500 kilohertz here. So let me reduce it. Now I'm going to reduce the input, and once you start seeing the yellow waveform reduce too, that means that you're within its range at this frequency. So, the yellow waveform's not budging, not budging, not budging. Ugh, God damn it. Stupid fucking analog discovery. Not budging. Now there we go. Okay, now it's kicking in. So now the amplifier is doing what it's supposed to do before, because otherwise it was just held hostage by the slew rate versus its actual gain. So that's why it wasn't budging, for so long. But the output's only like 3.6 volts peak to peak now, but it is looking like a halfway decent sine wave, but there's certainly some distortion evident. Even a triangle wave doesn't look so great, at 500 kilohertz. Um, Let me reduce its amplitude further. Son of a bitch. Okay, and but our gain is where it's supposed to be now. It's certainly 3. It's still at 3, still at 3. But again, it's not really a very good looking triangle wave. So, um, sorry about all the glare. But yeah, if you reduce it a little bit, it's still distorted as shit. I mean, I still wouldn't call that a very linear waveform, but we got less gain, loop gain to work with, but we still should have more than plenty with a gain of 3 on our amplifier. So again, not super impressed with that. And okay, at 1 megahertz, probably reduce our input signal again. Our gain's still 3, which is good, but it's certainly well-rounded corners for a triangle wave. Even the sine wave, you can clearly see distortion in it. Our output voltage is 1.75 volts peak to peak. Let me reduce it a little more. Well, what's it on square wave for? Okay. But yeah, I mean, I can definitely see some distortion in it, and you're also seeing some phase shift happening here. But that's about the maximum limit right there is 1.7 volts. But again, it's not looking all that great. But it's looking okay as a sine wave right now, with an output of about 1.3 volts. Let's increase the frequency further. Again, we should actually be able to go up to about 3 megahertz with this, at a gain of 3, before hitting unity gain. But our gain has already fallen quite a bit. Okay, but if I reduce it down to this level, we seem to be getting a gain of 3 again. we're still at a gain of 3, so we're still getting gain, but our output signal is now 400 millivolts peak to peak. And the further I increase it, see, we've already hit the limit. The yellow waveform is not changing when the blue one is, so that's certainly hitting its slew rate limit for this frequency. So yeah, about half a volt peak to peak is about the best we could do at 1.9 megahertz. And the TLO72, again, I could actually take out to 3 megahertz, just right around 3 megahertz, and still get a 1 volt peak to peak output signal that looked halfway decent. So let's increase the frequency further to about that same level, about 2.8, 2.9 megahertz. And let's zoom in a little bit so we can take a closer look. I mean, it looks like an okay sine wave, and our output's about 300 millivolts peak to peak now. So we've certainly lost a little bit of gain. It's still functional, but yeah, that's about the gain limit right there. So we can't get more than 300 volts, and you want to be definitely below that a little bit, because otherwise it's certainly going to result in distortion. Let's see. But our gain is about 2 now. So, and again, it should really be higher than that. But, maybe this op amp isn't up to spec, I don't know. But, yeah, gain's about 2.5, 2.6. So, at 140 millivolts. So, so evidently slew rate was playing some dirty games on us there. But let's just, for shits and giggles, see what happens if we go way up there to 5, 6 megahertz. At this point, my probes are, going to actually start screwing with us, because I got them to 1x. I don't want to go lower than that because our signal's down to 30 millivolts injected, so in fact, its peak to peak is actually only 30 millivolts, so it's supposed to be 60 millivolts. So, but we're at 7 megahertz right now, and it's hard to tell at this level with such low signal amplitudes how good of a sine wave this is. I mean, square wave certainly doesn't look any better on analog discovery or op amp. Let me see what happens if I go to 10x on the probes. I don't think it's going to do anything useful. Probably won't be able to see anything because of the noise. Yeah, I mean, there's just too much noise for that to be useful. Oh, look at that, a gain of 5. Okay, went back to 1x on the probes. But, I mean, I'm just not as impressed with the 5532 as I was with the 072, believe it or not. I mean, I really wasn't expecting much out of the 072. That's why I ended up making a pretty, kind of a long video about it, but I was mostly talking about DACs. But it certainly had superior performance overall, to this thing, even out to a few megahertz. I would say it was a superior device. But again, it's not terrible. It works. The first time I tested this damn thing, I forgot to put the decoupling capacitors, across its positive and negative power supplies to ground, and yeah, I was getting all kinds of weird noise and shit like that, and couldn't figure it out, because I don't have a lot of, I don't generally before these sets of videos. I mean, I've probably only breadboarded like 6 or 8 things in my entire life, so including some really elaborate complete Z80 microcontroller I built back in the mid 90s. That was on 2 really big breadboards, and I didn't have a spectrum analyzer, so I had to set up a bunch of LEDs to static stimulus step it, to as a means of a poor man's logic analyzer, basically, so I could do it with LEDs. The Z80 I had, you could static stimulus step, so you could run it at just incremental clock rates and advance it at your own desired rate, as opposed to some like Intel processors you can never do that static stimulus or static stepping anyway. because they got to run at a certain minimal frequency. Period. No ifs, ands, and buts. But but at any rate, yeah. I mean, I'm just not as impressed with this op amp though as I was with the the 072. So, um, but I mean, it works. Um, I'm just not sure what redeeming qualities it has. It's again because I'm still not generally impressed with what I'm seeing here generally. Um, it's not terrible. I mean, it's certainly usable op amp, but I mean, even for audio applications, because all over Elliott Sound Products website, they always badmouth the TL072. But I'm thinking, man, the 072 has a much superior bandwidth to the 5532, which they consider a halfway decent op amp, and I would have too before running these tests. But I mean, I gotta say, I'm really amazed that the 072 does as well as it does. So, which is good because I have a bunch of those. I got a bunch of 5532s as well. But yeah, I'm just really shocked, that, see, we're seeing some ring here at this level, 150 millivolts. Let's see if that increases with amplitude because we're still on a 2 volts peak to peak output. So we got some overshoot there, but it seems to be, that's a full-on square wave, a trapezoidal, tri, you know, trapezium, I guess they call it. Looks pretty good. I don't see any ring evident there. Um, see what the pulse looks like. Yeah, we got a slight ring, but it seems to be, um, damn it, maybe more automatic. It's ridiculous. Keep adjusting that shit all the time. I don't know if there is an automatic. I wonder if they have an automatic level on that. Nope. 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 Shit. Fuck. Oh, god damn it. I hate how this fucking thing does this. Now I don't know how to get it back. Stupid fuckers. Now I lost my other fucking thing too. I don't know how to get that back. Oh, son of a bitch. Yeah, there's a lot they did on Analog Discovery that's frankly really goddamn retarded. Um, this whole fucking thing is bullshit. I accidentally hit that all the time. You don't know how to get it back. Um, anyway, whatever. Okay, but yeah. Um, but yeah, trapezoidal looks pretty good and so forth. But yeah, the ring seems to be diminishing on the square wave. As we increase the amplitude, but it's certainly anything but straight. Well, we're only like 24 kilohertz here. You kind of expect almost perfect response out of this, but it's still less than ideal. And again, a lot of that's because of slew rate, but even the trapezium waveform is still got some slope to it too. So I guess you're going to have some of that for whatever reason, but still low frequency. You'd almost expect this to be perfect, and it's not quite perfect. Um, it's fine for sine waves though, and that's what most people care about, I guess. The triangle wave looks perfect. That's got a perfect slope to it. But yeah, I guess that transition is still kind of thinking of that as a slew rate thing. But yeah, but that's in the trapezium. Let's see what happens. But it doesn't really seem to level out or anything. See, it's still got a slope to it no matter what. So, I don't know. It's still, kind of less than I would expect, especially for 15 kilohertz. But at any rate, we're only at 11 volts too. I mean, um, peak to peak. I mean, I have it, half its level. Let's see, 14, 16, 17. Okay, 21 went too far. Okay, 20. Looks a little flatter here. That's just because it's a bigger voltage, I guess. But still, you know, just very curious behavior overall. So anyway, I just thought I'd, you know, kind of do a rundown on that and say that overall, I still say if you're considering one of these versus an 072, I take a really hard look at the 072 before making a decision despite its apparently inferior ratings. So, anyway, cheers.